Now I present the paper Climate Change and Automation, the Emission Effects of Robot Adoption, which was written together with Anna Abeliansky from the Austrian National Bank and Ernesto Rodriguez-Crespo from the University of Barcelona. As the motivation for a paper on automation, I like to present two pictures usually. This one is a car factory from 100 years ago. It's a factory of Ford as far as I know. And we see that production happens as we model it in economics, like a Cobb-Douglas production function. We have two inputs, human workers and physical capital in the form of this assembly line here. And there is a complementarity between the two. So the two combine to produce output. And without human workers, you could not produce any of this output here. So it was not possible to produce any output without any human labor input. Now, if we fast forward 100 years, then the picture that we get when we Google modern car factory typically looks like this one here, where we have industrial robots substituting for the human workers that we saw in the previous picture. So we have physical capital now in two different types. The traditional physical capital in the form of this assembly line, but in a more modern form than previously, and the industrial robots, a second type of physical capital that takes over the tasks that have previously been performed by humans in this picture here. Now, and this is for the first time actually in history that physical capital on its own can produce output in that way. That automation is a rather new phenomenon can also be seen in this picture here that presents the stock of worldwide operative industrial robots being kept track of by the International Federation of Robotics from the 1970s to the 2020s. And we see that the stock of industrial robots was negligible until the late 1980s. Then sluggish growth set in, but it was not until the global economic and financial crisis that the stock of robots really started to take off. So we see growth rates at the order of 10 to 15% per year since then. And the stock has quadrupled from about 2010. The consequences of automation have been analyzed in the literature quite intensively. So there is a lot on productivity and automation by Gretz and Michaels, Acemoglu and Restrepo, the first one more empirical, the second one theoretical, showing that productivity typically increases with automation. On employment, it's a little bit different. So Acemoglu and Restrepo in another famous paper from 2020 show that employment decreases due to automation in US commuting zones. But Dowd and co-authors do not find any such effects with the same method for Germany. And there are other papers like Mann and Büttmann and Gregory and co-authors who even find positive employment effects. So here the jury is still out. With respect to inequality, things are again more aligned. So the typical argument goes that it was until now particularly low-skilled workers that have been replaced by robots. So the robots were in competition with low-skilled workers predominantly, while high-skilled workers have even benefited from automation. You still needed the engineers to maintain the robots, you needed managers to run the firm, and of course they benefit if if productivity in production rises, and scientists who develop ideas and so on and so forth. So the high skilled are not substituted yet by industrial robots and could even benefit from them. Thus, inequality in terms of wages has been increasing due to automation. The labor share has been shown to decrease due to automation because the robots are in competition to the workers, but the income that they earn goes to the capital owners. So mechanically this decreases the labor share and thereby increases overall inequality because capital tends to be much more unequally distributed than labor income. So a decrease in the labor share mechanically increases income inequality. And then there have been papers showing how fertility can be affected by the deployment of industrial robots and also well-being in general. So well-being in terms of physical well-being or monetary well-being, but also in terms of psychological well-being. What has been investigated less, however, is the effect that automation has on emissions and therefore on the environment. There are some papers on this aspect that have shown that robots reduce the ecological footprint by Chen and co-authors, Li and co-authors, Chong and co-authors, and so on, and others that showed that robots increase pollution. Some studies have also focused on the city level. In China, Yu and co-authors, Wang and co-authors, and Song and co-authors, and some have found that lower energy intensity prevails and more green innovation prevails when there are more industrial robots. However, most of this literature really focuses on China, and what we want to contribute now is that we want to have a cross-country analysis of the effects of automation on CO2 emissions, and we want to provide a theory behind the effects that is then being tested empirically. We also need to consider the non-linearities in the whole context, because, as we will see later on, they are very important. We will show that automation can have different effects on CO2 emissions in early phases of automation adoption as compared to later phases. And we also improve on the estimation, taking care, for example, on the fact that many countries in the data of the International Federation of Robotics, even from 1993 onwards, report no robots at all. And if we do a standard log transformation, then of course we throw away these observations. So we also use an inverse hyperbolic sine transformation in one of the specifications, or in most of our specifications, to show how the results depend on that. So to summarize, our contribution and value added lies in 4 different points. So we provide a theory of the decision to employ robots in a firm and consider the emission externalities of robots. And this theory leads to 3 testable predictions that we then move on and test empirically on cross-country data globally on the relationship between emissions and automation. We will see later on that 2 of these hypotheses are very much in line with the data, and the third one is not. In so doing, we consider the nonlinearities that the theory predicts. We take a particular care of this nonlinearity, estimate this nonlinearity, and show that it is important. So omitting this nonlinearity may lead to biased results. And we address econometric issues such as the 0 entries in the robot capital stock. Now, after this brief motivation and introduction, let's go into the theoretical considerations. And the only assumption that we need is basically that humans need coffee to run smoothly, which we all know from experience, I guess, while robots require electricity and maintenance, and they need to be produced and so on and so forth. So based on this, it would be straightforward to assume that producing the same output, humans generate much less emissions than robots do. And then we assume that firm I in country J produces output at time t. So Y is output, I is firm I, J is country J, and at time t. With traditional physical capital, so that's the assembly line with an output elasticity of alpha. And then labor-like inputs, which can be human labor with a productivity of A, I, J, T, or the labor of robots, denoted by Z here, multiplied by B, I, J, D, their productivity. And these labor-like inputs are raised to the power of 1 minus alpha, so we overall have a Douglas production structure for producing output with this traditional physical capital combined with labor of either form, either humans or robots. So we capture both of these pictures here. This traditional picture basically of production, as well as the more modern picture of production. So now we can write down the profit function of the firms. So firms maximize their profits being given by the price that they can charge for their output multiplied by the output they produce. That's the production function. So the total, first term here is revenues of the firm. And then we have to subtract the cost of production, which is the outlays for wages. That's the wage rate in the economy. So there is no index I here, multiplied by the number of workers of the firm. So that would be the cost of production if the firms choose to produce with human labor. And we subtract the price of the robots that they buy. So PZJT is the price of robots multiplied by the number of robots would be the outlays for robots if the firm chooses to produce with robots. And profit maximization then implies that you take the derivative of this profit function with respect to the two modes of production that we are interested in here, either human labor or the robots, and set them equal to 0. And what we will see then in case of this perfect substitutability between human workers and robots is that firms will choose to employ humans if the relative productivity of humans as compared to robots is high, and if the reverse holds true, they would choose to employ robots. So if there is a continuum of firms, we can sort them in descending order of the relative productivity of humans versus robots, so A over B. And then a firm with a high level of A over B would produce with labor. This could be, for example, a firm in the textile sector, because it's still difficult to automate the tasks that are needed as inputs in the textile sector. By contrast, firms with a low level of A over B, so their robots are relatively more productive, they produce with robots and not with human workers. That could be, for example, firms in the automotive industry, or this Adidas Speed Factory that produced sneakers almost fully automated, and so on and so forth. And then, since we have a continuum of firms, infinitely many, there will definitely be a threshold level of productivity with a threshold firm that is exactly indifferent between producing with human workers as input and producing with robots as input. So we can compute the associated relative productivity of humans versus robots at which these firms are indifferent. And then we can calculate what happens if this marginal firm switches from the production using human labor input to production using robots as input. And in this case, we know that this marginal firm is there if there is, say, for example, a slight technological progress in the production with robots. So then the productivity of robots would increase slightly as compared to the productivity of humans, and that may shift this firm over the threshold so that it chooses to produce with robots instead of human workers. Now, if such a firm switches its production mode, then this firm would require ZIJT additional workers, which is, or ZIJT robots, sorry, which is the number of workers that it used before, multiplied by the relative productivity of humans versus robots. So that's intuitively clear. If the firm had more workers, you would ceteris paribus need more robots to replace them. And if the productivity of humans is comparatively high, then you would also need more robots to replace them. And that's, of course, considering a constant output level and a constant traditional physical capital stock in the short run. Now, the crucial question for us is whether the switch to production with robots generates more or less emissions. And for that, we let EIJLT be the emissions of a human worker in production, and EIJZT the emissions of a robot. And then it's reasonable to assume that emissions are externalities for the firm, because the firm doesn't really care whether the human worker drives to work by car or by train, or whether he lives close to the workplace or not. And the firm does not also doesn't care about whether the electricity it uses comes from a coal power plant or a hydropower plant or whatever. So the emissions generated here are externalities for the firm. And the reasonable assumption is that the emissions of the human in production are lower than the emissions of a robot, at least initially, because the robot needs electricity, the human does not. So then the emissions before the switch to robots would be the emissions of a human multiplied by the number of workers the firm has, and the emissions after the switch to robots are exactly the number of robots that you require to replace the human workers, multiplied by the emission intensity of robots. And that prominently features the ratio of productivity from between humans and robots. So we need to assess in general whether this term here is greater or equal or less than this term here, which is basically an empirical question as such, but I think from intuition one would assume that at least initially humans generate less emissions than robots. Perhaps then in the future robots will be so efficient that they generate less emissions than humans, but that's not yet the case perhaps. So this boils down to the question whether the emission externality of humans relative to those of robots is less than, equal, or greater than the relative productivity of humans versus robots. And that determines whether more emissions are generated after the switch than before. Now I illustrate this with the following graph. Here in this graph we have the relative productivity of humans versus robots on this line here. If this relative productivity is high, then the firm will likely produce with human workers. That's the textile firm, where it is difficult to automate production and so on and so forth. And if this ratio is low, for example, in the automotive firm, then this firm would produce with robots. Now there is this technological progress that changes the threshold here. I mean, we usually talk about the marginal change, but just for the sake of illustration here, I show this as a larger change. And then if there is such a technological progress, the threshold would shift to the left, which means that fewer firms would produce with human workers and more firms would produce with robots. So after this technological progress that increases the productivity of robots, basically, this threshold shifts to the left. So some firms that were previously producing with human workers are then below the threshold and produce with robots. Now the emissions that this generates is denoted by delta E, and it's likely to be positive initially, as I said, because robots produce more emissions than humans do. To summarize, this would boil down to the fact that the difference between emissions generated by robots and emissions generated by the equivalent amount of humans in terms of production input, that this is positive initially. Now, however, assume that we are in a different world where there has been a lot of progress in terms of automation. So the relative productivity of robots is has increased quite strongly. So in this case, we would be more to the left-hand side already. So a smaller fraction of firms produce with humans, and the larger fraction of shares still produces with robots. And then this switch may generate less, or definitely generates less emissions than in the previous picture here, because first, robots are more productive and replace more humans, and second, the more efficient robots will also generate less emissions typically, or need less energy input, electricity input, and so on and so forth. So in this case, the change in emissions is definitely lower than in this case, and it could even be negative. So we do not know a priori. And that's now leading us to the three hypotheses that we can test. The first hypothesis that we state is that robot adoption is associated with a rise in emissions on average. So that's basically an empirical question. The theory just tells us that both is possible, under which conditions it's possible, the theory also outlines. But to test the theory, we just pose this hypothesis that robot adoption is associated with a rise in emissions on average. More important is that this is nonlinear. So hypothesis 2 states that in earlier phases of the switch of production to from human workers to robots, this switch would raise emissions, and in later stages it may even reduce emissions. But definitely the effect is hump-shaped. So we would have a stronger effect on emissions in early stages of adoption than in later stages of adoption. That's what the theory clearly tells us. And as a corollary of the theory, basically, we would have hypothesis 3, that is that if a country produces its electricity predominantly with renewable power, with renewables that do not emit CO2, then this will definitely generate less emissions if they switch to robot production than in a country in which, say, electricity is produced by coal. And now we test these 3 predictions empirically. For this test, we use the following baseline regression equation, where we have on the left-hand side CO2 emissions per capita in country J at time t, and we take the logarithm of that. And we regress it on the logarithm of robots in country J at time t, and a number of control variables that are all kind of relevant in the context of emissions. Per capita GDP, it's clear, so income matters. There is the Kuznets curve relationship that we control for. Urbanization has been shown to impact emissions. Of course, industrialization, if the industry sector is greater, this typically leads to more emissions. And also, technological progress plays a role. If a country is more advanced, then typically technologies are more efficient. So we proxy this by the stock of patents and take the logarithm of that. And then in all of the specifications, we include either year and country fixed effects, or if we are interested in the trend, in the time trend, to estimate whether it's linear or non-linear, we also use alternatively to the time fixed effects the time trend. And to address the problem with the 0 entries for the stock of robots, we use the inverse hyperbolic sine transformation instead of the logarithm in every specification as a comparison to the specification with the logarithm. And then we check the robustness of the results with respect to the inclusion of additional control variables. For example, openness, trade openness, so that's exports plus imports divided by GDP, or financial openness, which is foreign direct investment and foreign investment outflows as a share of GDP. Institutions, where we use 2 different variables, different data sources for emissions, and also a different treatment of NAFTA countries, either including them or not including them, because they are always tricky to deal with in case of the International Federation of Robotics data, because for a long time these countries were not differentiated, so it was not differentiated among them, and the stock of robots was only reported for the aggregate of Mexico, Canada, and the United States. As data sources, we use the data of the International Federation of Robotics for the robot capital stock. We use, for most of the control variables, the World Development Indicators as a data source. And for the 2 types of institutional controls that we have, we take them from Kopec et al. From the Varieties of Democracy project. And as an alternative source for CO2 emissions, alternatively to the World Development Indicators, we take a recent paper by Jones and co-authors from 2024. Now, what are the results? Here we see the results from the baseline regression equation, where we have in column 1 and column 2 the results with fixed effects, time fixed effects, and in columns 3 and 4 with a trend that puts more restriction on the coefficients here, because it restricts the time variable to represent a linear trend. Now what we see here is that indeed there is a positive correlation between the logarithm of emissions and the logarithm of robots. It's significant at the 10% level. But if we take into consideration the countries that report 0 robots in the data, but still positive robots at some time in the data, then we get many more observations, and the coefficient on robots with this inverse hyperbolic sine transformation becomes more significant, so at the 5% level. What's reassuring here is that the coefficient size is almost the same, so it stays very similar, because there are many problems in interpreting this inverse hyperbolic sine transformation as an elasticity, but we see here that it's not very far away from the elasticity that we estimate in the first equation. So these 2 results would give credence to hypothesis 1, that on average the switch to robots is associated with higher emissions. However, and that we already see here when we look at columns 3 and 4, when we impose a linear trend, so when we kind of say, well, this is a hypothesis that only matters linearly and that there are no non-linearities in this whole consideration, then in the first column, the coefficient would become even insignificant. In the second column, so with the same but only a time trend here, the coefficient would only be significant at the 10% level and lower. So this already hints towards nonlinearities being important in the whole context. Before we come to the nonlinearities, however, we want to show that the results are quite stable with respect to introducing other control variables. So we have here in this table specifications where in the first two columns we use a different source for the emissions data. Then in columns 3 and 4 we included the NAFTA countries. And in columns 5 to 8, we include the additional controls of openness, financial openness, democracy in institutions measured in two different ways. In general, what we see, however, is across all these specifications, the coefficient is very close to the coefficient that we estimated before. Mostly it's significant. In the first specification, it's not. So overall, I think the lesson from that is hypothesis 1 is supported by the data in general, but there is a hint that nonlinearities could play a strong role. And we have hypothesis 2 that exactly takes into consideration these nonlinearities. So we test for these nonlinearities now in 3 different ways. First, we include dummy variables for the different countries in terms of whether they are upper middle income, lower middle income, or high income, where high income is the baseline category that we omit. For low income countries, we don't observe any robots in the International Federation of Robotics capital stock, so this category is anyway not in the data. And since we omit then the high income countries, all these coefficients here that include interaction terms between the corresponding income level of the country and the stock of robots is relative to high income countries. And what we see here is the interaction between robots and upper middle income and lower middle income countries that's significant and positive, meaning that they tend to emit more when they switch to robots as compared to the high income countries. Yeah. Now, also between these two, the middle income and the upper middle income and the lower middle income countries, we see the lower middle income countries have a greater coefficient size here, and it's significant at the 1% level. So indeed, it seems that this nonlinearity is there in a sense that early adoption in lower income countries tends to be associated with more additional emissions in terms of robots than later adoption in higher income countries. We do the same with the inverse hyperbolic sine transformation, that's column 2. We basically find the same, except for the fact that for upper middle income countries, the interaction with the stock of robots becomes insignificant. If we lump together lower middle income and upper middle income countries into one category, we would see that this category is significant in the regression with an average coefficient here, irrespective of the fact whether we use the logarithmic transformation or the inverse hyperbolic sine. So this first way of testing nonlinearities, including dummy variables for the income level of different countries, is basically perfectly in line with our hypothesis 2. Now, a second way of testing for this nonlinearity is if we include the linear term on the stock of robots and the quadratic term. That's what we do in column 5 for the logarithmic transformation and in column 6 for the inverse hyperbolic sine transformation. Irrespective of which we use, the linear term is highly significant and positive, highly significant at the 1% level. And the negative term is also significant at 5% in case of the logarithmic transformation and at 1% in case of the inverse hyperbolic sine transformation. So both of that are very much in line with a nonlinearity in the effect of robot adoption on emissions. And the third way of testing it would be to include a time trend again, and then interact this time trend with the logarithm of robots, or the inverse hyperbolic sine, basically. If we do this and use the inverse hyperbolic sine transformation, which we have in column 8 here, we indeed again find a positive coefficient for the stock of robots, highly significant, a negative coefficient for the interaction between robots and the year trend, again highly significant. In case of the logarithmic transformation, we do not find significance, but of course this may not be surprising given the lower number of observations. The coefficient size is again consistent with hypothesis 2. So to summarize, all the three ways of testing for hypothesis 2 indicate that nonlinearities play a role, and all of them support this hump-shaped relation between emissions and the adoption of robots that that the theory predicted, basically. Now we come to the third hypothesis, namely that the switch to the production mode of industrial robots is less polluting in a country in which electricity is predominantly produced by renewables. So we include the share of renewable electricity production in the regression, ln renew, and interact it with the stock of robots. Where is this? Here. And here we also have it in case of the logarithmic transformation, here in case of the inverse hyperbolic sine transformation. However, irrespective of which specification we use, we do not find a significant result here. However, the result that renewable generation per se reduces emissions is consistent with what we have here in this line, the negative coefficient that is highly statistically significant of the share of renewables. So this would imply that hypothesis 3 is not supported by the data. However, there is one possibility that could also play a role here, and that is that it may not be appropriate to test our hypothesis with the share of renewables in electricity production, because it's rather the marginal blend that matters, because we have this switch in the production mode, right? And this implies an additional electricity demand, and the additional electricity demand would be fulfilled by switching on another power plant, basically. So we would have the marginal plant that matters, not the average plant that matters. And it could very well be that in a country that produces 90% of electricity with hydropower, the marginal plant is a coal-fired plant that generates a lot of additional emissions, while in another country with only 30% of renewables on average, the marginal plant is a gas-fired power plant that generates less additional emissions. Then we would not see anything here, right? So perhaps this hypothesis has to be tested differently. So overall, we can conclude that robot adoption leads to more emissions on average. That seems to be, so that's the hypothesis that comes out of the theory and seems to be supported by the data. The effect, however, is nonlinear, that we have seen, that's also supported by the data. However, we do not yet find any evidence for hypothesis 3 that renewable electricity generation plays a role in the whole context. What do we learn perhaps from a policy perspective? Well, taking emissions into account is important, and they are an externality in this context. So this opens up a possibility for robot taxation that could be efficient. So robot taxation, as you know, is discussed up and down. Even the European Parliament discussed it at some point. Bill Gates has suggested to introduce it. Many papers have discussed robot taxation. But there are basically three main difficulties in this context. The first one is, how do you define a robot for the tax code, right? So perhaps a 3D printer would not be defined as a robot, although it still automates labor. So you may want to tax it as a country if you want to tax automation, right? Or a printing machine, printing press that substitutes for labor is also not defined as a robot, and many other issues there. Or if you have, say, If a firm buys 100 robots, it would have to pay taxes for 100 robots, but it's quite easy to claim, well, this is one integrated robot if you connect them somehow, and then you only pay the tax once. So that's the first problem. The second problem is that typically robot taxes would be inefficient because robot production is more efficient than production by humans, as we know, so it increases productivity. And if you tax it, then this would typically reduce productivity growth, so perhaps something that you do not want to do. And the third argument against robot taxes typically claims that if you introduce them in one country, then production could simply move to another country, and therefore you need international cooperation, and that is very difficult to achieve, particularly with robot taxes. Now, if you tax instead the emissions that robots generate by taxing emissions in a country, then first of all, this would be an efficient tax in the sense that it is on an externality, and if it reduces the externality, this would move the country closer to the optimal solution. So this argument would be that it's more efficient taxation. Then it taxes robots indirectly via emissions, but then there is no need to define a robot because the tax on the robot just depends on the electricity requirement of the robot. So we do not need to define a robot in any way. So this problem would simply disappear. And finally, it seems to be easier to coordinate on an emissions tax, which we have in the European Union, for example, across the countries, than it is on a capital tax. Like a tax on robots. So all these three reasons are usually mentioned against robot taxes, but taxing emissions would indirectly tax robots to some degree and would be an efficient tax and a tax that is easy to administer. It already exists. There is also much easier coordination. And future research should basically have a look on the emissions of artificial intelligence, because robots may have more or may emit more than humans, but where there is really a lot of emissions going on and a lot of electricity demand is in artificial intelligence, where, for example, training large language model costs or requires the electricity that a small town requires per year, or also a query for ChatGPT costs 10 times more in terms of energy input than a query for standard Google query and so on. So therefore, it would be important and interesting to analyze the emission effects of artificial intelligence. Well, thanks a lot for your interest. Thank you very much for watching the video. I hope you found it interesting and useful. For more economic content, please visit my channel that you see on the left-hand side here, or follow one of the closely related videos that you see on the right-hand side.